Hi, in my previous video I talked about half-wave rectifiers. Are there only half-wave rectifiers? No, there are also other types of rectifiers like a full-wave rectifier. Let's roll the intro. In my last video, I said that a rectifier is just a device that converts alternating current into direct current. Then what is a full wave rectifier? A full wave rectifier, unlike a half wave rectifier, does is that it converts both the half cycles. That is the negative half cycle as well as the positive half cycle will be converted into a pulsating DC signal. Let's dive deeper. A full wave rectifier needs multiple diodes. Generally, we have two types of full wave rectifier. One is using a center tapped transformer and with some diodes. There is also another type of full wave rectifier using four diodes called a full bridge rectifier or a bridge rectifier. So the first one is using a center tapped transformer. It's not a big deal. It's just a transformer which have an additional wire connected to its center of the secondary coil. No, it's not a transformer, it's my hand. This is the schematic diagram of a full wave rectifier using a center tapped transformer. This is just an alternating current source. These are two power diodes and this is just a load. And this is the center tapped transformer and this is the additional connection which I have mentioned. So what happens is that the alternating current always moves back and forth. So when I apply the alternating current, the current will first pass through this diode without any interruption because the current is in the forward bias condition, but it will not pass through this diode because it is in the reverse bias condition, so it will block the current. So it have only one way to go, so it will go through this load and it will complete this circuit. So in the next negative half cycle, the diode will allow the current to pass through because it is now in the forward bias condition, but this diode will block the current because it is in the reverse bias condition. So it have only one path to go, so it will go through this load and it will complete this circuit. Next we have the full bridge rectifier. In full bridge rectifier, we generally use four diodes connected in this manner called a bridge. I don't have the required transformer. Anyway, in full bridge rectifier, it is not necessary to have a transformer like the previous one. Then why am I bothering about a transformer? It is because I don't want to get killed by a 120 volt or 230 volt or 240 volt, depending on your country. This is the schematic of a full bridge rectifier. This is an alternating current source. These are four diodes and this is just a load. If you look at the circuit carefully, you can see that these two diodes which are highlighted with red color are pointing towards that direction, and these two diodes which are highlighted with brown color are pointing towards this direction. So what happens is that when I apply a voltage, the current will pass through this brown colored diode only because these two diodes are in the reverse bias condition. So if a current comes in this way, these two diodes will block the current, so the current cannot pass through it. So the current will now only have one choice, so it will flow through this load and it will also flow through this brown colored diode and it will complete the circuit. So in the next half cycle, wait, if you recollect about that wasting guy, the half wave rectifier, he wastes either the positive half cycle or the negative half cycle. He's not like that. He's a good guy. He never wastes anything. So in the next half cycle, the current will pass through the red color diode only because now the brown color diode is in the reverse bias condition. So if a current comes, it will not pass the current to flow through it. So now the current will pass through this diode, I mean this load, and it will also pass through this red color diode and it will complete the circuit. So this is how the output DC waveform from a full bridge rectifier would look like. If you remember the output waveform from a half bridge rectifier, it would look like this. You can see there is no voltage or any signal here. It is because this half bridge rectifier is actually wasting this negative half cycle. But here you can see there is also some sort of waveform here. It is because it is actually using that negative half cycle or the positive half cycle. From this itself, we can say that a half-wave rectifier wastes a lot of voltage while a full-bridge rectifier, he's a good guy. He doesn't waste a drop. Hey, you liar! Sorry, I forgot to say that this guy also weighs a tiny amount of voltage, about 1.4 volt. It is because the current is actually flowing through two diodes in the first half cycle itself. So a diode has a voltage drop of 0.7 volt. So multiplying it by 2 will give you 1.4 volt. But it's not a big deal. It doesn't waste as the half wave rectifier does. These full bridge rectifier circuits are also used in your phone chargers. I have seen people doing videos on how to make a phone charger circuit. They are actually making these full bridge rectifiers and claiming that it's a phone charger. Please don't do that stupid thing because first it doesn't have any protection. It can kill your phone pretty quickly. And it may work for some time, but it will affect the battery's capacitance, its performance, and its overall lifetime itself. Always charge your phone with its own charger. In my previous video, I have talked about smoothing capacitor. A smoothing capacitor is just a capacitor which smooths out the output DC waveform. So if I connect a capacitor with my circuit, the produced output waveform would look like this. It is much more pure than the output waveform produced by a half wave rectifier. It is because in that case the capacitor does have a lot of time to discharge, but here the capacitor have a less time to discharge, so the produced output waveform would be much more pure. And that's it. Thank you for watching. This is me, Dev Prakash. I'll catch you in the next one.